Well, let's begin. I'd like to welcome you all today to our foam control webinar. It's a series of webinars that Brenntag puts on periodically, usually on a quarterly basis, focusing on various water treatment applications throughout the water treatment industry. My name is Kevin Cope. I'm the Business Development Application Specialist for Brenntag North America. I will be your host today, kind of walking you through some things and introducing our presenter here in a few moments. In the past, as I mentioned, Brenntag has done a number of different webinars, ranging from heavy metals removal, anti-scalants. So previously, we've done a foam control webinar in conjunction with the AWT. Some of the other ones are successful jar testing, successful biological treatment, mastering the art of dissolved air flotations. And our most recent webinar was mastering the art of clarifier operations. Now, each one of these webinars, with the exception of the heavy metals, has been recorded and is available on YouTube for your viewing. So just reach out to me when the webinar is over, and I can send you a link to every one of the webinars that we've conducted to date. We're also extremely proud of the fact that we have been awarded certification by the AWT, Association of Water Technologies, for CEU credits for their CWT program. Basically, the requirements are to view the video of a webinar, a video of one of the webinars, request and complete a certification exam, score 80% or higher, turn the certificate. Once you do that, turn it back into to me, and I will issue a certification certificate. It is then presented to the AWT for CEU credits. And again, to get the webinar link and also the exam, contact Kevin Cope at brenntag.com. I'm very, very excited today to have one of our water additives managers, specifically Jacob Barrios from Brenntag Southwest. I actually got to spend last week with Jacob in Nashville, and we discussed this webinar quite a few times. Jacob, as I said, is the water industry manager for Brenntag Southwest. Obviously, he attended the University of Houston and wanted to say go Cougars. Jacob has been in the water treatment chemical industry for about 10 years, starting with the chlor-alkali and in water treatment. And I will apologize if I've called him Jason. It is simply because I have been working with a Jason all day yesterday and today. So Jacob, I sincerely apologize. Jacob started his career in the municipal water, focusing with a company called Altivia. And when he wrote this down, I started chuckling at first. He said, it drinks lots of water. Well, it took me a few minutes to realize that the water he's very experienced in drinking contains some hops and yeast and a few other things. And I'm sure he'll talk a little bit about that today. I did get to meet him and meet his lovely wife last week. I had met her the year prior in Nashville, but we got to spend some time together this week, and loves hanging out with his wife and his 3 dogs. And so when he's not working. So with that, Jacob, take it away, and we'll begin.
Hey, thank you very much, Carl. Kevin. But firstly, I'd like to thank everybody for taking the time out of your busy schedules to join us today. I know everybody's got an agenda that they'd like to stick to, and so I appreciate everybody being here. But speaking of agendas, we'll go into what we're going to talk about today. First, we're going to start with foam creation, the different types of foam, how you control foam, the methods of testing for foam, different field applications, active markets foam control is used in, and then move into any questions that may come up during the presentation. So, what is foam? To define it, foam is a dispersion of a gas, most commonly air, in a liquid, most commonly water. And because we're water treaters, this is often our thought as well. But it's important to note that water is not the only liquid that foam can occur. As Kevin mentioned a little while ago, beer is a great example of that. Beer is not just pure water. It's a mixture of proteins and carbohydrates and hops and yeast and so on. So, I want you to keep that in mind as we go through this presentation. And we're not necessarily just talking about water. Sometimes you'll hear us reference liquids and so on. So yeah.
Sorry, my computer is frozen. There we go.
Okay, so foam control applications. Here are the many different areas where foam is present. You have the water treatment areas, and you also have the specialty applications in different industries such as paper, paints and coatings, cleaning industry, and so on. But for the sake of our presentation today, we mainly want to focus on the water treatment areas, primarily cooling water, wastewater, processed water, and the municipal sector. So why control foam? There's a lot of reasons that you'd want to do so, but I think one of the top at the list is that it's not aesthetically pleasing. Nobody likes to see foam, and I think a lot of people, when they see it, they think that it's a concern. Other reasons: you can get discharge fines, some as large as $50,000. It also causes operational safety problems, such as slippery floors. This is a big one to us here at Brenntag, as we have, a commitment to safety, and we pride ourselves on providing an environment to our employees and their families by minimizing these dangerous conditions. So controlling foam here at Brenntag is always on our mind. Another thing is that foam can drift from one area to another. It can land on areas where it can cause larger issues, such as being corrosive to paint on cars in a nearby parking lot. It can also provide production problems. A great example, I think, of that would be in a plating shop. Let's say that they're plating different types of metals, and if there's foam present, that foam can actually provide a barrier on the surface of that metal to where you can't plate it like you're supposed to, or it could cause issues down the road. So what causes foam? If you remember back to our definition we talked about previously, foam is a dispersion of a gas in a liquid. So, you absolutely need agitation or turbulence the majority of the time, and also a foaming agent such as a surfactant. In the example of the beer that we kind of touched on earlier, this foaming agent would be the proteins, the yeast, and the hop residue that's present in the beer that causes it to foam. But, something that we need to make sure as water treaters that we're all mindful of is the fact that pure liquids, something like distilled water, is not going to foam. You need to have these other foaming agents, such as surfactants and things like that, present for your liquid to foam. So, while we're on the topics of surfactants, I'll kind of touch on the different examples of surfactants that we typically see. There are many anionic, such as soaps of fatty acids, sulfonated materials, phosphate, ethoxylates, and then you have the quats and the non-ionics, ethoxylates as well. So why do surfactants cause foam? In order to understand that, you first have to understand what a surfactant is. So surfactants are relatively low molecular weight molecules that have a hydrophilic or a water-loving side and a hydrophobic or water-hating side that causes them to orient themselves on the surface of a bubble that produces an elastic film which helps form that bubble wall, referred to as a lamella. And that lamella helps prevent the bubble from rupturing. So below is a small little illustration of a surfactant showing the hydrophilic side, which is the water-loving side, and the hydrophobic side, which is the water-hating side. So this slide here is to kind of help paint a picture and give you a better example of how a surfactant will align itself in the water and in the air, which will ultimately cause the foam to be created. So if you look at the picture on the right hand of the slide, the surfactant has positioned itself with that water-loving or hydrophilic side that we were talking about in the water, and the water-hating side or hydrophobic end in the air above the surface line. So here we have a body of water that has no surfactants present. When we have no surfactants present in the water, the air will simply come from the bottom up through the top, and no foam will be created. So moving into the next slide here, what happens when you have surfactants present? So unlike the water that has no surfactants in it, when we do have surfactants, they'll position themselves with those hydrophilic water-loving ends in the water and those hydrophobic water-hating ends out of the water, ultimately causing for this layer of foam to come to the top and spread across the surface, as you can see here. So the first kind of type of foam that we'll talk about is surfactant foam. So, if you're having a foaming issue and you see that the foam is white, it's kind of irregular in shape, as you can see on the picture off to the right here, it's a pretty good assumption that what you'd have is surfactants present in whatever the liquid is that you have. And, this picture here, I think, shows it pretty perfectly. Moving into the next slide here is another example, and this is more so the biological foam. So just like the white foam in the previous slide, here on this one, we see tan or brown colored foam in the picture off to the right. So generally speaking, if you have a tan to brown color foam that has almost like a dry shaving cream-like appearance, it's most often caused by the microorganisms in the water breaking down the organics. So, this foam is generally very stable. Like I said, it's got a dry shaving cream-like appearance. So if you come across something like this, it's pretty safe to assume that, biological microorganisms could be the cause. So when we're talking about foam, there's usually about 4 different types of foam that we commonly talk about. The first one is entrained air foam. This is foam that hasn't yet reached the surface of the liquid. Then we have microfoam, which are very, very tiny bubbles. Next is impinged air. These are particles in the water, such as dispersed solids that have air attached to them. And the last foam that we have here on this slide is dry foam. Dry foam is just like it sounds. There's less water and more organics present. This one, like we touched on earlier, can be pretty tough to treat because getting your defoaming agent to it can be a challenge. A good example of this would be foam buildup on the side of a tank. So here's a quick history of foam control. So the first defoamers were things like kerosene, fuel oil, and other light oils. These items were most commonly used as they would float to the top of the liquid that they were introduced to, therefore knocking the foam down. In the 1950s, they started experimenting with the silicone-based defoamers. In the early 1960s, we had our first defoamers with hydrophobic particles. In the early 70s, we started to see oil-based hydrophobic waxes. And in 1973, when the oil crisis hit, it caused an issue in the industry because these oil-based defoamers began to be too expensive. So what ended up happening as a result to that is that moving towards the end of the decade, water-based defoaming agents were starting to be introduced. A very important bullet on this slide here is the second to last one. That's 1989. That's the year I was born, just in case any of you were wondering. And then moving on to that, we saw in the early 90s, silicone emulsions started to hit the scene. So defoamer or anti-foam? That's kind of the age-old question, isn't it? So let's first run through the definitions of each of them, and then we'll talk briefly about them. So firstly, a defoamer is a substance used to reduce or eliminate the amount of a foam that's already present. That's kind of the key part there. Reduce or eliminate foam that's already present. An anti-foam is a substance used to prevent the formation of foam from ever occurring. So a defoamer reduces or eliminates the amount of foam that's already present, and an anti-foam prevents the formation of foam from ever occurring. So one of the big key things to realize here is that the chemistry of each of these items, a defoamer or an anti-foam, are typically the same or very, very similar. So that goes back to the previous question. Is it a defoamer or an anti-foam? I think the key takeaway here is that the products are generally the same. It's when you add them that makes the difference. So defoamer or anti-foam, these are often interchangeable. And I think that, through the course of this presentation, I've done it a couple of times myself. Okay, so this slide here is a great slide to help everybody understand the difference between defoamers and anti-foams. So just to kind of paint the scene, the picture on the right is a picture of a stream near my buddy's house where a sewage treatment plant discharges. So every so often, this stream will have a 20-foot by 1 foot or so ripple of foam that's coming out of the sewage plant's discharge right outside of the picture. Somebody, a passerby, a local resident, will drive by the stream, they'll see the foam, they'll freak out, they'll call the sewage plant, and they'll complain. We see a bunch of foam in the river. So what do the folks at the plant do? They'll go outside, they'll turn a pump on, and they'll feed the product until this foam in the stream goes away. This is general practice and happens the majority of the year. However, once a year, they feed this product 24 hours a day, 7 days a week. Why do you think that they do that? Well, the reason why they do it is because it's trout season and they can't have any foam present in the stream because of the fishermen out there fishing. So the key takeaway that I want everybody to get from this slide here is that it's the exact same product that the operators go out there and turn on periodically when passerbys complain, or the one that they're feeding 24/7 during trout season. It's when you feed it that makes the difference. So knockdown and persistency. These are a couple of the key terms that you'll hear about when we're talking about defoamers. If you ask which one's more important, most folks would probably say both. The next couple of slides are going to cover these two terms here. So knockdown, by definition, is the ability for a defoamer to reduce, remove, or kill an existing foam. There are a couple of key parameters that I think we all need to think about here. It's speed and thoroughness. So how fast do you need the foam to be knocked down? Do you need it done very quickly, or is it something that can be done more gradually? And how thorough of a job do you need to do? Do you need to knock the foam down a little bit, or do you need to completely kill it and get it out of there? So generally speaking, how fast an operator wants the foam to be knocked down depends on their particular situation. So to kind of touch on an example here, let's think that, you were a hotel owner and there were some little hoodlums at your hotel and they dumped a whole bottle of dish soap into the fountain in the front of the hotel. If you were this hotel owner, I bet you'd want that foam to be knocked down pretty quickly so the hotel doesn't look unsightly. So, different scenarios are going to come, with different levels of this, but it's something to keep in mind. So persistency, persistency refers to the ability of an anti-foam to keep foam from reoccurring. The two key parameters here are time and thoroughness. When we're thinking about time, how fast does the foam come back? Is it coming back quickly or slowly? And how long before it reoccurs? And when we're talking about thoroughness, is it maintaining all or just some of the foam? A really good example for this going through something similar on the knockdown was like, let's say that you own an amusement park, and in the amusement park, you had a water ride. Good chances are that the folks running the park would want to keep an anti-foam in their water to prevent any foam from being created. Foam's generally unsightly, and you don't want the park goers to be concerned with the quality of your water and your ride. So that's something to think about there. So going into this slide, defoamer spreading action. So when you add a defoamer to your system, as you can see here, bloop, we just added the defoamer. You want that agent to spread quickly across the surface of the system and ultimately begin to provide both a chemical and physical knockdown of the foam. So when we're talking about defoamers, what we want out of a defoamer is for it to penetrate the wall or the lamella, like we talked about earlier, of the bubbles that are present. So this is pretty much exactly what defoamers are designed to do. Defoamers actually contain, on a microscopic level, particles that essentially cut the side of the bubble, allowing for the trapped air or gas to escape up and out. So as you can see there in the little graphic example. So types of defoamers. When we're talking about defoamers, there's usually a couple types that we talk most commonly about. On the left here in the picture, in these milky looking ones, we have dispersible, soluble, or emulsifiable. And on the right, we have the insoluble products. So just to kind of touch on this, if you remember the story and the history of defoamers that we talked about earlier, when you look at the picture on the right, you can start to get an idea as to why some of the early defoamers that were used were products like kerosene. You have foam on top of the liquid that you're trying to treat. The kerosene floats to the top and it knocks down the foam. So, it kind of makes sense when you see it like this. Excuse me. So which kind of defoamer would you use in the field? Well, if you're trying to decide whether you need a soluble or an insoluble product, you got to think of a couple of things. Soluble defoamers are typically better at passing through obstacles in the system. If you have some hard to get to areas, and they'll give you more full system control, and they're great anti-foaming agents. So conversely, insoluble defoamers aren't quite as good at passing through the obstacles in the system, but they're generally better at treating focused areas of foam, and they're great for defoaming. So the takeaway here is that if you need foam knocked down quickly, an insoluble product would probably be used. And if you're trying to prevent foam from occurring, you would use a soluble product. So here's the different types of defoamer chemistries readily available. We have the silicone-based, the oil-based, synthetics, both oil-free and ester-based, and the water-based products. So which factors most affect foam? Firstly, we have the chemistry of the water. Then we have solids. Are there any solids in the water? And if so, what types of solids? Then we have the pH and the temperature of the water. And also, what are the system parameters? Do you have a large or small amount of agitation, a lot of obstacles in the system, and so on and so on? So walking through each of these factors, the first one that needs to be questioned is the chemistry of the water. What is the foaming agent that you're using? What products are currently in the system, and so on. So solids can impact defoamers in quite a few different ways. Questioning how consistent the solids in the system are is very important. For instance, if you get a lot of solids on a regular basis, you'll generally have more foam than if you had less solids in the system. So that's something to keep in mind. So pH is another thing to be mindful here. Generally speaking, the higher the pH, the more that foam can and will occur. Also, if your pH levels are way outside of the normal ranges, the pH can actually chemically attack the different components in the defoamer, which would ultimately cause the defoamer to not perform as advertised. Temperature is another one. They have a large impact on foam as well. Temperatures above 140 degrees Fahrenheit, water-based defoamers tend to not be quite as effective. And if you go below 45 degrees Fahrenheit, you can have issues with product dispersion. So, I'm not sure if we have any of our Canadian friends here on the call, but we have a nice little conversion for you to Celsius if you were curious. So system parameters, last but not least, different system setups can absolutely cause foaming. So you have to be aware as a water treater, what are the different factors, such as, the obstacles in the system, what kind of agitation and where is it occurring, and retention time. So here's the most common, defoamer components. We have silicones, silica, amides, mineral oils, and so on. So whenever you're trying to decide, which type of defoamer that you're going to use, you have to consider, where you're using it, because certain defoamers have component restrictions into certain areas. So just to kind of touch on a few of these here, with silicones, you're going to want to avoid using those in metal plating and metal finishing. A good example of that would be, if you're working in a paint shop and you're painting cars. Silicone-based defoamers can actually lay, a thin layer on the surface of, say, a car panel or a hood or something like that. And when you go to paint, your paint won't get good adhesion, and that can cause issues down the road. The next one here are mineral oils. So, if you're discharging into a stream or into a waterway or something like that, you're going to want to make sure that you make sure that you don't feed mineral oil based defoamers, because what will actually happen is it'll start to cause a sheen on top of wherever you discharge to. And the last one here is, if you have an RO system, you'll want to ensure that you're feeding defoamers that don't have particles, as they can actually blind the membranes in the RO, causing issues down the road. For RO systems, there are defoamers that do not contain particles, so you want to keep that in mind, and just make sure that you're using one of those if there's an RO system, at the facility. So when it comes to testing foam, there's three common ways that we see most often. We have the shake test, the airstone test, and the foam cell. And moving forward, we'll kind of touch on each one of these a little bit. The first one is the shake test. This is good when you're in the field and you're looking for a quick and dirty way to get an idea of what product you'll need. The test is pretty straight to the point. The problem is that it's not perfect. Essentially what you do is you put the liquid that you're testing into a clear bottle, you'd shake it, and then you'd add the defoamer to see how well it performs. If you were testing for an anti-foam, you'd simply add the product in prior to shaking. What this test really does is it gives you a rough estimate of which product to use and how well it performs. So the next test here is the test that many people prefer. It's actually called an airstone test. So from a field standpoint, it's usually quite a bit better than the shake test. It does take a little bit more equipment than the shake test, but it allows a more precise measurement of the amount of foam created and the amount of product needed to control it. So in order to perform one of these tests, you'll need a few things. You'll need an aquarium air pump, you'll need some tubing, some aquarium air stones, generally speaking a stopwatch, or these days an iPhone, I suppose, and a graduated cylinder. So, the biggest benefit of this style of test over something like the shake test is that when you're using the shake test, it only tells you if the product works or doesn't work. An airstone test not only tells you if this information, but it also tells you how much product you'll need and how much it controls the foam. If you drop a little bit in there, how much does it knock it down? So you can see a more precise measurement. One thing to keep in mind is that if you're testing all day and you're using the airstone test, you need to make sure that you bring more than one air stone with you, because as you're dosing your defoamer throughout the day, what will actually happen is that defoamer will go into your air stone. And what you'll realize is that towards the end of the day, you'll need less product and you're having, it's performing better, and that's because it's absorbed into that air stone. So just something to keep in mind. The last test that we'll touch on here is called a foam cell test. So this is a test that's generally not used in the field. It's used more frequently in lab settings for very critical applications, or more often for product development and things like that. It's a great test because it offers a lot more control than the prior two tests we talked about. But for our purposes, it's generally not always needed, and it can sometimes be overkill, to be honest with you. So, test parameters. When you're running your tests, the important things to think about is, what outcome are you looking for? Are you looking to completely reduce the foam or only temporarily reduce it? How quickly are you looking to reduce the foam, and how persistent do you want the foam control to be? You also need to remember those component restrictions that we had touched on a little earlier. Are there any certain types of defoamers that you can't use in this particular application? Is it a plating shop? Is it a, it could be a handful of things. So you need to keep those things in mind. So, when we're testing, we need to make sure that our method of testing reflects that of the system that we're trying to treat. So knowing when foam control, or knowing when foaming occurs, can be incredibly important. If you find that foam pops up every Wednesday at noon, maybe the plant cleans every Wednesday morning, and a lot of surfactants are being added into the system, creating this foam. So knowing whether another thing is knowing whether the defoamer is soluble or insoluble is a great thing to consider. So as we kind of touched on earlier, certain systems may have more obstacles, and an insoluble product may be preferred as it'll reach those harder to get areas. Maybe they only have one problem at one area, and they need fast, direct treatment that a soluble product can offer. So the product must be compatible with the system. So when dosing defoamers, you should keep in mind that, as water treaters, we typically feed them neat. Water can absolutely be used as a carrier, but there's really not a whole lot of need to dilute defoamers. But with that said, one of the most important things to consider when treating foam is that we want to feed the defoamer as close to the problem area as possible. We also need to touch on the system characteristics, such as weirs and spray bars and feed locations and things like that, because they definitely play a factor here. So here on this slide are some of the more common water treatment areas that foam control agents are being used. So, we have them in cooling towers, of course, wastewater, municipalities like we've been focusing on. But we also see them in mining, refining, just general industry, the paper industry, absolutely, chemical, many others. We see them, used heavily in food and things like that. So, there's different markets that they're commonly being used and should be considered. So that pretty much wraps it up for today. I appreciate everybody's time. And if there's any questions that have come through, Kevin.
Well, we did. Jacob, there were a few questions that came through, so let me get started with those real quick. You mentioned, one of them said, can you talk about the spray bars you had mentioned during one of the slides?
Oh, sure. So, typically with the spray bar, they're used to do a couple of things. In a system, they not only deliver the foam control agent as close to the area as possible, but at the same time, they actually, offer some physical knockdown of the foam, just by, spraying it directly on top of the foam. So, one of the things that we talked about today is that we want to make sure that we get the defoaming agent as close to the areas that we're trying to treat as possible. So one of the things that I've seen personally is that, you know, if you have a large lagoon or pond that you find is foaming, and, you know, if you were to just add the defoamer in the corner of that pond or that lagoon, you know, it'll take quite a while to disperse throughout the pond. You know, but if you have spray bars that are, you know, spread throughout the lagoon, you know, it'll not only help you get, you know, your product more closely to the problem area, but it'll also help physically knock that foam down. So spray bars can be extremely helpful and beneficial, you know, if you have the resources and the availability to have them.
Very good, very good. Another question came. It just basically said dry foam. Any suggestions?
Okay, so dry foam is one of those ones that can be kind of tough. You know, in my experience, you know, dry foam what'll happen is it'll get stuck on kind of like tank walls and things like that. And so if you're feeding defoamer into the water, you know, or the liquid that you're trying to treat, you know, that water is not going to magically go up the side of the tank. So you kind of have a couple of options. You can basically scrape the foam off the side of the tank, you know, use a brush or something like that and push it down into the liquid that has the defoamer in it. Or what you can do is you can put the defoamer into something like a pump sprayer or, you know, some sort of thing that'll allow you to kind of broadcast it out, and you can spray it directly onto the foam. So that's kind of the two options you have when treating dry foam.
Yeah. And then last one, you mentioned about the air stone test. Can maybe speak a little more why you like that over the shake test?
Sure. Yeah, I think, you know, the biggest benefit over the shake test is that, you know, the shake test only tells you if a product works or not. You know, it's really tough to dial in how much of a product you need. And just kind of to put it into, you know, an example, you know, let's say you take a sample and you put in, I don't know, 100 mils of water and you put your air stone in and, you know, you run it for 5 minutes and then you start dosing product in. You know, if you started with, I don't know, let's say 2 inches of foam on top of that, and you were to dose in, I don't know, however much defoamer, you can actually make a report and you can say, okay, I put in this much defoamer and the foam was knocked down X amount. And then you can say in 2 minutes. And then you can say, okay, I dosed in this much more, and then all the foam went away after another 5 minutes. So it really allows you to not only see if a product works, but come up with a more detailed report that allows you to make product recommendations, you know, dosing recommendations, and so on. So it's really a great test, and as water treaters, I think it's one that we should keep in our back pocket, you know, for when the time arises.
All right, very good, very good. There is one last one here. I can take it if you want me to. It's something I've
Sure.
actually experienced with. The question was, how effective is feeding the defoamer into the influent of an aeration basin? It really can be effective. I've actually done that at a few steel mills. I'm from the Pittsburgh area and I've had experience doing that. Jacob had also mentioned about the spray bars. In one of the cases, they did have spray bars. The other one, they did not. It really boils down to how big, and no pun intended here, it really boils down to how big the lagoon is, the feed location, how effective the product is. I've seen it be effective. I've also seen it be somewhat of a miserable failure. So anytime you can cast the defoamer out more into the basin over a wider area, it can always help you quite a bit. So hope that answers the question, but that's at least one of the experiences I had with some of the steel industry applications in the Pittsburgh area.
Absolutely. Good stuff, Kevin.
Thanks. Well, that really right now concludes, hang on one second, folks, concludes what we've done today. There will be a video available of this webinar. It takes a few days for that to loop around and I can get it and put out there. There will be a PDF version also available. Either contact me at kcope@brenntag.com with your needs, and we will make sure we get those out to you. And very much like to thank you all for joining us today. Jacob, excellent job. I apologize for calling you Jason earlier, but Jacob, great job. And like to thank again everybody for attending our webinar today. Thank you.
Yep, thank you.